we can hear you.
Oh, okay. So my name is Alexey Glushko, and I am a master degree student in the Sergei University. And today I want to present our work, Interactive Research Toolbox for Chemical Compounds Analysis based on well-interpretable models. So my talk will be divided in two parts. Oh, excuse me, how can I actually swap slides? Oh, okay, thank you. So first section is technical section. We will discuss tools that we was created and some architecture of these tools. And in the second section, I will explain how we actually use these tools on our field experiments that were given for us from Mireia Russia Technology University. And what data science results we can reach with these tools. So in the next slide, you can find motivation for this work. I think everyone here knows that nowadays ML methods in some kind of hype train, and there is a lot of works applying different ML methods to chemical data. But if we will look how this data is actually collected, how field experiments is made, there are a lot of problems with this. Because our colleagues use some manually work for collecting these data sets, and it's quite hard. So we decided to make some system that can actually make life of data scientists and field experiments a bit easier. So this system is called Research Toolbox. And on the next slide, you can see some use cases of the system. So the main goal of the system is give a chemist opportunity to input data from the field experiments and pre-process it in a friendly way. And for data scientists, this system give opportunity to run the models on clean data and make it easy to run models in the clusters, in computational clusters and clouds. So and both roles can analyze results of computational experiments and field experiments and compare them side by side. So as for requirements for the system on the next slide, you can find that we hardly want our system to support computational experiment methodology for making it as user-friendly for our colleagues from Mireia University as possible. And of course, we want to be open source because it's cool nowadays, actually. So on the next slide, you can see our architecture. We start with a Nomad architecture. It's quite well-known research toolbox, but it uses some enterprise components. So we replace them with open source one and make front end a bit more user-friendly for our colleagues, and also made a data model for them. So data model is actually the point of interest for us. On the next slide, you can see part of this data model. This part was made for our first demo field experiment that we will discuss a bit later. Important thing here is connection with ontologies, because we want to save these connections for making our system able to explain data that it has. So actually metadata is important. And we research different ontologies that we can use in our system. On the next slide, you can see a list of these ontologies. For now, we stick with 3 ones that have a bold font. It's Hem font ontology for chemical compounds and CBI taxon for organisms and ontology of units of measure. And this combination of ontologies, nice interface for inputting and processing data, and well-created async workers for running models can give us opportunity to faster and more accurate made computational experiments based on our colleagues' field experiments. On the next slide, we will go to the computational experiment section. So here we will show our demo example. Our colleagues from Murray University give us some data from the experiments on antibacterial activity. On the next slide, you can see how this experiment was actually made. So they grow some microorganisms in Petri dish, then created holes in this Petri dish, and put some chemical compounds there, and after 1 day count area of microorganisms stop growing. So we call this area stunting diameter, and this is a target variable in our data set. Our colleagues asked us if we can find out which of the features of chemical compounds and bacteria give more influence to stunting diameter. So our first step was with little data set. On the next slide, you can see characteristics of our data set. We have only 99 experiments. It's quite usual task for field experiments because it's hard to make a huge amount of field experiments. So we usually have little amount of data. And also these experiments are split on two types. When we use chemical compounds in salt state and in solution state. And we have only 4 bacteria with 12 features for this experiment. So it's kind of a lot of feature and not so a lot of data. So we need some models that can process this data. And on the next slide, you can see actually models we chose. We decided to go with quite well-known models based on decision trees ensembles. And this is random forest and gradient boosting from Escalon package and XGBoost. You can find links in the bottom of the slide. These models can easily produce importance of features. We calculated it by weights. So we just calculated how often feature is applied in trees in ensembles, and this metric was our contribution to prediction of this feature. First experiment was made on some kind of mixed data set. So we just take all experiments, no matter it's solution or salts, and train our model. From this experiment, we want to find out if our model can actually put salt and solution flag as the most important feature to our contribution, because it's a kind of not so correct experiment because we mix salts and solutions. So we want our model to make a correct splitting, and our model actually could do it. So here you can see that salt and solution are the most important feature. And in our next experiment, we decided to split our data set. On the next slide, you can see another proof for this action. We go with a little amount of data because we split our data set into 2 parts. But because of very different area of stunted diameter distribution, we should definitely do this. And this improve a bit accuracy of our models and also produce more interpretable results. So on the next slide, you can see feature importance of the random forest models, you can see that the most important feature is crystal structure of the salt and electronegativity by Oganov. And the next slide, same experiment for solutions. And here also electronegativity of Oganov is one of the most important features. We also calculated metrics for our models. On next slide, you can see a table with metrics. It's important to note that we use grid search for hypertuning our models and use five-fold cross-validation in our grid search. So here you can find some MIS scores, MSES scores, and explained variance scores. That's quite not so bad actually. As for my yes score, it's about 10% of target variable, so it's actually okay results. But we didn't choose what model to interpret it based on our metrics, because usually you can find that models with better metrics is not always better interpreted. So we proceed all 9 plots from our model side by side, and we reached that electronegativity and crystal structure is top feature of importance, and we show this result to our chemist colleagues, and they actually was happy with these results because they some kind of waiting for them, because they also made some chemical research and can reach approximately same results. So they give us some more experiments. They made this in the next slide. You can see in one slide more, please. There's some parameters of our model. Hey, can we go to the next slide? Yeah. Oh, yeah. So this is characteristics of our extended data set. We have now more experiments related to salts, but we also have more bacteria. And this is very nice because in previous results, you can see importance of bacteria's features, and we hardly want to find out actually what bacteria feature is the most important. So we add more variants to bacteria, and also add some new features to chemical compounds. On the next slide, we can see that why we add some features to chemical compounds. The point is that electronegativity can be counted in different scales. On the next slide, you can find these 3 scales. It can be counted by Aganov, by Melikan, and by Pauling. And actually, these scales can produce different results in our models. So we want to discover 2 things. First of all, in new data set, we want to find out which bacteria feature is the most important. And other thing, we want to find out which electronegativity scale is the most important. So we go with some new model in our system. On the next slide, you can see tables that compare different combinations of scales and compare them with 3 our main metrics. Yeah, and we do these calculations for salts and for solutions. On this slide, you can see table for salts. On the next slide, you can see table for solutions. And okay, I think we jump through one slide. Yeah. Oh, yes, thank you. And you can see that metrics is approximately the same. So we can't from this data be sure if one scale is better than another scale. So we decided, okay, maybe scale by its own can produce some good results, but what if we use electronegativity scales with some constant features from salts and solutions that will be added to all combination, all like 7 combination we have. And we did this experiment. The next slide, we can see feature importance by random forest for whole souls dataset with different scales. And from here, we can see that model thinks that electronegativity by polling is more important. On the next slide, you can see a table with different combinations and constant features from souls. So here you can find that combination with polling init have better metrics. And this is quite nice. We can make a hypothesis that polling scale is better for souls. And as for solutions, on the next slide, you can see that feature importance is quite nearly the same. A bit Aganov scale is better, but this is not so sure result. So we decided to make some combinations with it on the next slide. And you can see actually that Aganov scale in terms of explained variance score is better than others. Yeah, so next slide, please. Yeah, so from here, yeah, explained variance have no zero value or only for Aganov and no electronegativity at all. So so we go from here with 2 hypotheses that polling and Aganov scale are better for our task, polling in terms of solves and Aganov in terms of solutions. And from the and then we decided to add some bacterial features to our combinations. We also want some feature importance of bacterial features. And on the next slide, you can see, and next slide, please. You can see that our model reached to find out that Gram-Stein positive or negativeness of bacteria make a huge contribution to overall predictions. And this thing we can reach only with extending of variety of bacteria we tested. And it's quite good result because Gram-Stein positive and negativeness show what kind of layers we have in our bacteria and its structure, and of course it should make a huge contribution to our prediction. But as for electronegativity scales, they have quite nice contribution, but working approximately the same. So on the next slide, you can see a table with different combinations. And we can see that Aganov and polling scales have a bit better metrics, but actually the difference is not so huge. So let's go to the next slide and see what we can reach for Gram-Stein bacteria. We can find out that Gram-positive bacteria are more sensitive to our research compounds. And let's conclude all we said before, like all our results. On the next slide, we have 2 kinds of conclusions. Next slide, please. We have some data science results that we've shown to our colleagues, and it's results that electronegativity have a huge influence to our target variable. It's also results that Gram-positive bacteria are more sensitive to our research compounds, and that polling and the Aganov scale, and that we can make hypothesis that polling and Aganov scale are slightly better than Millikan scale for our task. And as for technical results, all data science we discussed before was made by our system. So we reached to simplified input and output process of field experiment data, and simplify communication between data scientists and chemists. So we think this is our main contribution in technical point of view. And of course, we will develop our system in the future. On the next slide, you can see our future point of works. We want to add some more model support, especially we are waiting for FCA model because they can be much more interpretable than our current ensemble decision tree models. We are working on a new test case based on titanzol, based on titanzols, and we are also looking for support for deep learning techniques, because now it's a slightly hard task because of needs of some GPU workers and so on. So we will definitely release our system in open source in the future when we reach our first milestone. So thank you for your attention, and I think we can go for the question in the next slide.
Questions. One question. I, as a chemist, love the estimation of the quality of machine learning using mean absolute error and mean squared error. But my colleagues from information technologies prefer the measure coefficient of determination. Why did you not use of this approach to estimation of quality of machine learning experiments?
We actually used explained various score for some kind of this task, but I think you are talking about something like R squared, yeah, metric.
What is value coefficients of determination in your machine learning calculations?
Actually, for now, we working on this metrics. You can see only we calculated only 3 of them for now. That was shown in a slides before. So, yeah.
I use this by feature electronegativity in my machine learning experiments for prediction of properties of inorganic substances. But this feature is no so informative in comparison, for example, ionic radii, for example, Shannon-Prewitt radii, and pseudopotential radius of Alexander. And these radii values usually are most informative in comparison of electronegativity, for example, Pauling or Batsanov or Melikin and so on. Why you uses by this the good feature for forming of your feature description?
Actually, we have used our ionic radii too, and in our experiments, electronegativity, in our models, electronegativity showed better performance. So I think it's hardly depend on models we actually discussed, because as we mentioned, to find out that electronegativity have not linear dependency with stunting diameter. So I think it's because of using decision trees models, they're able to work well with electronegativity scales. So
thanks. Yeah. Another questions.
So you mentioned using cofantologies.
Yeah.
Can you explain a little bit in more details? So why do you use them? Do you modify them, or you just use them as is? So, and what is the benefit of using the ontologies in your case?
Of course, we modify them. We add some methodology of field experiments to them, and some like knowledge of of our current experiments. And the main benefit of them for now is just kind of description to our data. Yeah. So we use them mainly as handbooks. But for future, we want them to use as a some source of boosting our ML models pipelines. Yeah.
So do you use them as just dictionaries, or you somehow?
Yeah. For now, it's just dictionaries and some I don't know some base for future models. Yeah.
Okay, thank you.
Okay, questions?
Well, I've got a question, if I may. Okay, so Alexander, you have told that actually you are building a kind of a toolbox which consists of a number of well-interpretable machine learning models. But what do you mean claiming that these models are well-interpretable? Because from the work, actually, it's obvious for me that you are measuring somehow feature importance, and basically that's it. So then the question is, how would you define that the machine learning model is well-interpretable?
We made some like decisions that model for us, for our toolbox, it will be well interpretable if its result can be understandable and interpretable by our chemist colleagues. So we for now measure feature importance, because there's like task they want from us, and show our results, and our results were quite understandable for them, and they can make some chemical conclusions for them. So that's it. Of course, for future, we will go with some more classical approaches like FCA that have better interpretation.
Okay, but then in principle, it turns out that any model can be well interpretable by your definition. I think that we can call machine learning models fundamentally interpretable, I mean, well interpretable, if we can basically understand how this model arrived at the specific decision. If we can't understand this, then how we could claim that model is well interpretable? So I think that you should elaborate on this a bit.
No,
yeah,
okay,
that's just a general comment. Yeah, because from my feelings, feature importance is not enough here. So we should definitely have something more. Yeah, thank you.
Yeah, okay, of course we will work on this. Thank you for your comment.
Yeah, thanks.
Next